All right, all right, all right. We got ourselves a little bell work. So, I am going to go ahead and write a few things in here. So we got the probability of A and B occurring is 0.1219. Wasn't that wonderful? So this is 0.1219. Then it has the probability of A occurring is 0.53. So how do I write that in? Because I can't just write 0.53 in the set A. Really, it's 0.53 minus that overlap of 0.1219, which gives me 0.4081. And the same concept will apply for the probability of B. So I'm going to take the total of B and subtract out that overlap, right, the intersection. And I'm going to get 0.1081. So that's how I'd fill out that wonderful Venn diagram. But I also have the outer part to deal with. So if I take all of my probabilities of 0.1081 plus 0.4081 plus 0.1219, I get 0.6, so all those added together is 0.6381. I do 1 minus that, and that'll give me the outer part. So I would just write that, say, right here. That's not a very good point. 0.3619. Cool. So I could have, also I could have just added together 0.53 and 0.23 and subtracted out one of the overlaps because it'd be like overlapping twice. So could have done that, but you would get the 0.6381. Okay? All right, lovely. I'm going to work out the second one here, and just pause. You can pause the video, try it, and I'm just going to pop the answers up. All right, so here we go. We've got all of our Venn diagram filled out. So remember, A or B occurring. I realize that maybe you guys aren't too familiar with that. That's just basically saying, like, as long as it lands somewhere in there, we're good. All right? So if it lands in set A, if it lands in set B, or in the intersection, all those are good. That means all of that is 0.8. So I used that 0.8 and subtracted out the 0.37 of B to get just this portion, right? Like the part of a moon portion of the Venn diagram. That gave me the 0.43. And then since all of this is the 0.8, I can subtract that from 1 to get my 0.2. Cool. So when we're going to be dealing with conditional probability here, and that is determined after an earlier event has already occurred. So given that this happened, what's the probability that this happens now? So like, given Mr. Allen has decided to shop at Costco, what's the probability that he picks up a gallon of milk? I don't know. Something like, that's what I'm thinking here, right? Given that one event occurs, probability of the other thing happening. So now we're going to get into the lovely notation here of conditional probability. Mr. Ordachenko has joined the room.
What's up?
There he is. All right. So this notation up here is saying what's the probability of event A happening given that B has already occurred. Okay? That's what this bad boy is saying here. Probability of A given that B has occurred. All right, so our regular old probability is all of our elements of A divided by the entire dealio, right? That's the entire set here, right? So just A over the whole thing. But as we get into the conditional probability, oh, look at that beautiful erasing job. It is like flawless. All right, so now we're saying what's the probability that A occurs given that B has happened, right? So probability of A given B has already happened. So we basically have to erase everything that's not B. Really, we're erasing all of this as well, right? We're only thinking about what's in set B. So that changes our wonderful probability. We're going to explore that, aren't we, Mr. Rodachenko?
We are.
Fantastic. So here's how it's written. We've got our number of elements in A and B divided by everything in B, right? So we're basically just changing what we're looking at. And we will deal with that with actual numbers, actual probabilities in some of these Venn diagrams and also in tables as well. So we can also flippy-floppy here, ladies and gentlemen. So now we're dealing with the probability of B happening given that A has already happened, right? So same kind of deal. We're looking at the elements of A and B, which is the intersection. That was a slight voice crack. We're going to leave it in there. And then we're dividing by everything in set A because that's what we're looking at, is just given that A has already happened, that's our denominator, and our intersection of the two in the numerator. All right, so here we go. These are the two basically formulas we've already written down, but I want you to jot them both down. So the probability of A given that B has happened, and the probability of B given that A has already happened. All right, so they look very, very similar. Just really our denominators are the things that have changed.
You're doing a really great job. This really is holding up.
Thanks, Mr. Rodachenko.
You haven't made a mistake yet.
I know. As long as I have you by my side, I feel anything is possible.
Anything.
All right, so let's think about this bad boy for a sec here. We've got conditional probability and independence. So as we know, for the probability of A given that B has happened, it's the probability of A and B all over the probability of B. Now let's think about what this looks like as we use some of our other wonderful formulas. Probability of A and B, as long as they're independent, is just the probability of A times the probability of B. And if we're still dividing by the probability of B, my goodness, what happens here, Mr. Rodachenko?
Looks like they cancel out there.
Whoop! That's fantastic. So I'm just left with the probability of A. So they're not affected by the whole, well, if this one occurs, it doesn't really change the probability because of that cancellation that's going to happen. Right? So it doesn't really affect it with independence. Anything to add, Mr. Rodachenko?
I think we need some examples.
Some examples.
Let's get some examples.
That's right, examples. Like math samples at the Costco, right? What's your favorite sample at the Costco, Mr. Rodachenko?
Oh, it's got to be those little mini tacos.
Ooh, mini tacos. Big fan of those. The other day I had some spinach artichoke dip or whatever it was on the naans, the mini naans, and that was fantastic. I went back 3 times. I put my hat on backwards and forwards and then took it off so they wouldn't recognize me. And then I drew a mustache on my face. It was fantastic. All right, it's time for some examples. So we're flipping a coin and then picking a marble from a bag, which are 2 independent events. Would you agree?
Yeah. Why are they independent?
Well, if I flip a coin, does that change what's going on in that bag of marbles that you have?
Absolutely not.
Absolutely not. Really, we just should be questioning why somebody's carrying around a bag of marbles. But anyways, so if a bag of marbles contains 2 purple, 1 green, and 2 orange, what's the probability of getting heads? And if you knew that a purple marble had been selected first, which would be written as probability of heads, given that you've selected a purple marble. Well, the probability of getting heads is 1 out of 2, right? And a purple marble, since there's 2 of them and a total of 5, we got 2/5. All right. So, Katoa, math joke. The probability of A and B would just be the product of those 2 probabilities. So 2/10, or what does that simplify to, Mr. Rodachenko?
Looks like 2/5. 1/5. I'm good at math.
He's good at math. There we go. All right, so 1/5. So the probability of A, given that B occurred, would be the probability of A and B divided by B. Now, if we write that out with some numbers, I've got the probability. I know this looks disgusting with all these fractions. Actually, you know what? It looks fantastic, right?
I love fractions.
I love fractions. So we've got 2/10, or 1/5, as Rodachenko had said. divided by the probability of B, which is 2/5. Well, if you remember math rules with multiplying or dividing fractions, you multiply by the reciprocal. So this becomes 5/2. So we get 10 over 20, which would then simplify to 1/2. All right. Well, that means that flipping a coin and getting heads is still 1/2. Thus, the purpley dude did not impact it, did not affect it. That's
That makes it independent.
oh my gosh, makes it independent. Like free Americans, independence, land of the free, home of the brave. All right. So the probability of A, given that B occurred, is probability of A. Thus, these are wonderful independent events. That's just fantastic stuff right there. More examples?
More exams.
All righty. So from this bad boy over here, this diagram, we can determine that probability of A happening is 0.25. How do we get that? Well, we added 0.15 and 0.1. Now, I feel like something else is maybe missing from this diagram. Mr. Ochenko, do you have anything to add here?
Well, stuff that's not in A or B is not named yet.
So everything that's outside of those. Well, how do we figure that out? What should everything add up to, Mr. Ochenko?
Everything should add up to 100% or 1.
1, and then we would want to basically subtract the sum of 0.15, 0.1, and 0.3. So if we math this out, are we at 0.45?
Looks like 0.45.
All right, we'll see. We've got 2 math teachers here. You never know if we can make a mistake. That's probably hard to see that 5.
We might have made a mistake. Don't put the equal sign with the U. The universal set's not 0.45. The stuff outside of the circles is 0.45. Looks great.
There we go. Look at that. Just working together. Making math and memories.
Teamwork.
Teamwork makes the dream work, children. All righty. So, if event A and B are independent, then having B happen first would not change A, right? And vice versa. So let's see here. If A happening given that B has already occurred equals A, we can show that they're independent. If it doesn't, which is right down here, if they are not equal, then they are not independent. All right, so how do we figure out probability of A given B? Well, if I find out the probability of A and B and divide it by the probability of B, we get ourselves 0.25. Lovely. That's fantastic.
I've seen that number before.
Indeed. Indeed. All right. So my probability of A, we already had written up here, is 0.25. Probability of A, given that B happened, 0.25. My goodness. What's going on here, Mr. Artichenko?
Those look like the same number.
Woo, woo, woo. So they are indeed independent of each other, all right? Because one does not affect the other. Probabilities are equal when we have probability of A or probability of A given that B has already happened. So since the probability of A given that B happened does not change the probability of A, B has no effect on A, independence. America. All right, last one here. Ooh, a table. A table of iPods and smartphones and not smartphones. This is great. So we can just go ahead and start, maybe jotting some things down, taking a look here. So we've got ourselves the probability of, let's just say, an iPod. I'm going to jump down to the second one real quick. Probability of an iPod. What would that be there, Mr. Artichenko? Looks like I've got 28 iPods.
28 people have iPods. 50 people were surveyed.
So 28 over 50?
Yeah.
I dig it. What about just having a smartphone?
Well, 38 people have smartphones. 50 total people. It's got to be 38 out of 50.
Excellent. And then I'm going to jump back up to the top one. I don't know really why I decided to skip it, but I feel like the and was maybe like, what? Well, iPod and a smartphone. That looks like it's, I'm gonna switch up the color here. We're going to go red. iPod and a smartphone is the 20.
20 out of 50?
Woo! Let's find that intersection, you know what I'm saying? Good stuff. Where they crisscross. All right. So now we're looking at what's the probability of it being a smartphone given that it's an iPod, right? I believe that's what the SP is, smartphone, given that we've already established that it is an iPod. All right? Well, the probability of iPod and smartphone we know is 20 over 50, and the probability of an iPod is 28 over 50. So I can divide those two. And what do we do when we're dividing with fractions, Mr. Odachenko?
Use your calculator.
Or
Multiply by the reciprocal.
flip-flop. That's right. We're going to multiply by the reciprocal. So 50 over 28 instead of 28 over 50. And when I simplify that, we end up with 20 over 28 for the probability of a smartphone, given that an iPod has already occurred, right? That event has already occurred. We're saying that it's an iPod at least. Now, what does that tell us here? Well, what's the probability of a smartphone?
38 out of 50.
38 out of 50. Is that the same as 20 out of 28? I think not. So the probability of a smartphone and the probability of a smartphone given it's an iPod are not equal. Thus, they are not independent. One affects the other. Now, my esteemed colleague over here, Mr. Odachenko, during a brief intermission, has brought up a wonderful other way to look at this. Mr. Odachenko, you want to dive in here?
Yeah, let's try it. I've never used this app, so let's see what happens.
Let's get the laser. I'll get you the laser going.
Laser?
Yeah, laser.
I want to box it in, though.
Oh, okay,
So,
you want to box it.
Right here, this box that I'm trying to make
Make the box.
is all the data that we need to know because I'm already given that an iPod has already occurred. So the spots with no iPod, no longer important, and the 50 total people, no longer important. So my total sample space is 28 people. Shows up right there. People with an with the smartphone already shows up there. So you don't even have to use fractions. You could still use the table.
Indeed. That's with the table, ladies and gentlemen. That's pretty dope. That's two ways to do the same problem.
Ooh,
Two for the...
low probability.
Oh, yeah. Mr. Thornley just entered the room. The Thorn Dog. All right. You guys have yourselves a wonderful day.